In this video we are going to extend our discussion on U-substitution, this time looking at definite integrals instead of indefinite integrals. So we have the same kind of setup. We've got some function on the inside that we are not able to just simply take the antiderivative of, and so we're going to make that substitution so we can do so. But that's also going to change how we actually evaluate the definite integral at the end. So I'll go ahead and hopefully this first part is not new because we've done this with indefinite integrals. So we need to figure out what we're going to let u equal, and that is going to be the inside part of our square root in this case. So we're going to say let's let u equal 2x plus 1. And then we have to determine du. So we take the derivative of that. That's just going to be 2 dx. Now I don't have that random 2 in here with this, so I want to go ahead and think of this as I'm going to divide by the 2, so I get 1/2 of du is equal to dx. Now with an indefinite integral, that's all we did, and then we went ahead and rewrote this and evaluated. So I'm going to go ahead and do that part, but then I'm going to need to talk about something else that's going to change. So we have an integral. We now know that we're looking at the square root of u du, and we're going to put the 1/2 out front. So I'm replacing the dx with the 1/2 du, and I'm replacing the 2x plus 1 with just u. Now, what I haven't messed with yet are the bounds, the a and the b here. So the 0 and 4, if you think about evaluating an integral, you plug those values in for x at the end to evaluate. So these are bounds in x. Those are x values. So we now have an integral where we don't have x, we have u. So what I want to do is I'm going to say, in addition to figuring out u and du, I'm also going to say, how can I change these bounds to u values, right? So if x is 0, I'm going to use this definition of what we're letting u equal. U is 2x plus 1. So if x is 0, u is 1. So I'm going to change this bound to 1 because that's now my u value that represents x being 0. And I'm going to do the same thing if x is 4, then u would be 9. And now I can go ahead and evaluate this. And in changing those bounds, I don't have to go back to x at all. So with an indefinite integral, when we did U-substitution, we would take the antiderivative and then we would go back and plug back in what x was. If you change your bounds, you don't have to do that. So I'm going to think of this as u to the 1/2. So I can do my antiderivative, square root. I'm just changing that to u to the 1/2. I'm going to go ahead and evaluate the integral. So I'm going to do the derivative. So this is going to be u to the 3/2, and then I would do 2/3 of that, but I also have this 1/2 out front. So 1/2 times 2/3 is going to be 1/3. That's going to be my constant out front. And I'm just going to evaluate that from 1 to 9. Again, those are u values, 1 and 9. I don't have to go back and replace u with 2x plus 1. I'm going to leave it as u, and I'm going to evaluate this as is. So we're going to have 1/3, and I can just bring that 1/3 out front of the entire thing. So I'm going to do 1/3 of 9 to the 3/2 power minus 1 to the 3/2 power. And that's going to give us 1/3 of, let's see, on the inside here, 9 to the 3/2. So that's the square root of 9, which would be 3 to the 3rd power, which is 27, minus 1 to any power is 1. So that's going to be 26 on the inside, which means our final answer is going to be 26/3. And I didn't have to go back to x at all. So I will say that you can leave your bounds as 0 and 4, but at this point where you take the antiderivative, you would need to replace u with 2x plus 1, and then I could leave this as 0 and 4. The mistake that people make most often is that you leave it as u, you don't go back to x, but you forget to change your bounds. And if I evaluated this at 0 and 4, I would not get the same answer. So I need to make sure that I'm changing those. Okay, so let's look at a couple more examples here. Number 2, it's a little bit confusing. I'm going to bring this dx out to the side and then put just a 1 on top, and maybe that'll help us a little bit here. But I'm going to let u be the stuff that's inside the squared function, so 3 minus 5x. So du is going to be negative 5 dx. Again, I don't have a random negative 5 in there, so I want to think of this as negative 1/5 of du is going to equal dx. And then I'm also going to change my bounds. So if x is 1, then u is negative 2. And if x is 2, then u is negative 7. Now, we like to, when we have integrals, have the smaller number on bottom and the bigger number on top, because that represents, from, it makes sense, it's left to right, right? So it's from a smaller number to a bigger number. Now, in doing this, it's actually going to change here. The 1 becomes a negative 2, and the 2 becomes a negative 7, which is a smaller number than negative 2. It's totally fine. Okay, you don't have to change the order of that. You can. There's a property out there that says you can change those if that bothers you. You just have to put a negative out front, and if you wanted to do that, that would be totally fine. I'm just going to go with what we have here. So I have the integral, and again, I'm going to go from negative 2 to negative 7. I'm replacing the u is replacing the 3 minus 5x, so I'm going to have 1 over u squared. 1 over u squared. And then we're plugging in negative 1/5 of du for dx. So I'm going to have du here, and we're going to have negative 1/5 out front. And that's our integral. So I'm going to then take that as negative 1/5, the integral from negative 2 to negative 7 of u to the negative 2nd du. And I'm going to evaluate that. The negative 1/5 will stay. And then we have u, we're going to add 1 to the exponent to the negative first. And then we're going to divide by that new exponent, which would be dividing by negative 1, which means that negative 1/5 is simply going to become a positive 1/5. So I have 1/5 u to the negative first, and we're going to evaluate this from negative 2 to negative 7. That means we have 1/5 times negative 7 to the negative first minus negative 2 to the negative first. And if you evaluate that, you get 1/14. That's your final answer. Okay, last one. This one's a little bit tricky with what we're going to let u equal, because I don't really see, hey, this thing was plugged in to this other function. But if I rewrite this just slightly, I think you'll see it. If I rewrite this as the integral from 1 to e, so what I have is the natural log of x divided by x. I want to think about that as the natural log of x times 1 over x dx. Right? If I just do times 1 over x, it's the same as dividing by x. And I see that this 1 over x, that is the derivative of the natural log of x. So if I let u equal the natural log of x, then du is going to take care of everything else. The derivative of natural log is 1 over x and then dx, so I'm going to replace all of that with just du. And then we'll change our bounds. If x is 1, u is, well, what is the natural log? Again, we're using this. What is the natural log of 1? That is 0. If x is e, then u is the natural log of e, which is 1. We actually get a really nice integral here. We're replacing natural log of x with u, so I just have u here. 1 over x dx is being replaced with du, and my bounds are now 0 to 1. And this became a much nicer integral to evaluate. So I just do the antiderivative, 1/2 u squared. We're going to evaluate from 0 to 1. So I'm going to get 1/2 of 1 squared minus, if I plug in 0, I get 0, which means we end up with just 1/2. Okay, so that's a case where U-substitution was really nice to us because it took something that was a little bit complicated to work with. Like, most students don't like to work with natural log of x or plug in an e as a bound or anything like that, but in doing so, in using U-substitution, we got this very simple integral to solve, which is very nice. So again, same initial steps as indefinite U-substitution. You need to figure out where you're going to let u equal. Find du. Hopefully that takes care of the other stuff inside the integral. But then the key difference is making sure that you change your bounds to u's so that you can go ahead and evaluate that definite integral.